Hello, welcome to this video on accepting sampling plans. In this particular video we're going to discuss the computations for the operating characteristic curves and how that relates to or can be used in the design of the sampling plans. We are going to use Excel, but first we're going to see a couple of examples. So let's see. In the previous video, we discussed this table and how we use the computation of the binomial distribution to estimate the sample size that we would need, given that we had, in the previous video, we saw this table and we demonstrated how the binomial distribution was used to estimate the sample size if we wanted to achieve a particular level of probability of acceptance. In this example was 95% across all the options, and the sample size would change if we had an acceptance number that was defined, and also saw that there is a trade-off in terms of how fast we can eliminate or reduce the beta probability, the probability of error type 2, which is the probability of accepting lots that we should not accept. And but we didn't do all the actual computations. We are going to make some sensitivity analysis now, so we have a better understanding. There is in this table, the parameters are color coded. So what it's in green is related to the alpha error, although in some of the tables is presented as 1 minus alpha, the 95% probability of acceptance. Beta is in purple. The proportion of non-conforming at 12% is shown in blue, and the proportion of non-conforming original 1% is shown in red, and where those parameters go into the formulas. So let's go see the computations. To compute the operating characteristic curves, we have to have a clear understanding that the probability of accepting a lot depends on the values of the proportion of non-conforming. If we accept that some of the product will come by natural variability out of specifications, and we are willing to accept that level of non-conformities, we call that P, and a particular sample size for inspection denoted by N, and the acceptance number is C, then the probability that the number of defects that we will find being less than or equal to that acceptance number C can be computed by the binomial distribution. The equation for the binomial distribution is familiar to us by now, and it depends on the combinations of how many different ways we can arrange X elements in N total. That times the probability to the power of X, and 1 minus b to the power of n minus x. We are particularly interested in the cumulative probability from 0, in this case 0 non-conformities in the sample, all the way to the acceptance number. And so all of these possibilities, if the acceptance number is say 3, we can have 0 non-conformities in the sample, 1 non-conformity, 2 or even 3, and still would accept. So the probability of accepting the lot is the cumulative probability of the binomial from 0 to C, and that is expressed in that equation. So that's what we're going to use to compute our OC curves. Here you have some results on the computations of the operating characteristic curve. In this particular slide, the acceptance number C is fixed at 2, and we change different sample sizes. We have sample size of 5, 10, 20, 30, and 40. And we also changed the proportion of defective. So you can see here that the proportion of defective varies from 1% to 12%. And if the sample size is only 5, with acceptance number C equals 2, then there is very little change. We will accept most of the lots because there is a little chance, very small possibility that we will find 2 non-conformities in a sample as small as 5. However, if we go to the sample size n equals 40, you will see that the probability of accepting the lot, that is the probability of having 0 or 1 or 2 non-conformities out of 40 is 99.25 when the proportion of defective is only 1%. However, the probability of having 0 or 1 or 2 when the proportion of defective is 12% is only 12.61%. And the reason for that is because now there is a higher chance that you will find more than 2 non-conformities in the sample. And the larger sample size would reduce the chance of accepting these more defective product. So if you compare the n of 5 and the n of 40 columns, you will see that the slope is steeper for n equals 40, and that means that we reduce faster the probability of accepting lots that are coming worse and worse. And that's closer to what we really want to have. We want to have a good decision criteria that allows us to identify when this is happening. We can alternatively fix the sample size, and when we fix the sample size, in this case 40, we can change the acceptance number. And in this example, we are varying the acceptance number from 0 to 3. And now you can see that in the case that we have an acceptance number that is higher, we are more permissive, naturally speaking, because even if we find some non-conformities, we still accept in the lot. And these two behaviors are the trade-offs of what we need to identify as a good combination of N and C. Of course, if we consider our first table, let me go back there. If you consider this table, we made the computations all the way to 137 in order to obtain an alpha of 5% when the acceptance number was 3. And there is a trade-off on the cost, because inspecting 5 units is going to be very different from inspecting 36 units or inspecting 82 units or 137. So now I'm going to switch to Excel for you to see how the computations are made. Very good. We are here in Excel, and before I go into the computations of the operating characteristic curves, I need to point to different tools that you have in Excel in order to facilitate the work. The first one is you have embedded some of these distribution formulas in Excel. Actually, there is more than one implementation of them in the system by default. So if you have, say for instance, the number x as the number of successes, and you have n the number of samples, and p the probability, let's just consider an example here. Let's say that the number of successes is 2, the sample size is 30 and the probability of success is 1%, then we can compute the probability of acceptance of this plan as the binomial. Well, it's not the probability of acceptance right now, it's just the probability of being equal to x. So probability of x, let's see, right there, probability of x is the binomial distribution. Now you see, as I type in binom, you have several options, and all of them are implemented. Some of them are pretty much equivalent, others are just a little bit variations for you to work with. So we have the number of successes is the first parameter. 2, the number of trials or attempts or the sample is 30. The probability is 1%, and then the next parameter is asking if you want it cumulative or not. If it's just a probability of having x equal to just 2, I would have to write false or 0. So the probability of having just 2 is 0.03283. If I want to compute the probability of x being less than or equal to 2, now I can compute in the same fashion, binomial dist, with the number of success still being 2 and the trial still being 30, with the probability still being 1%, but now the cumulative would go with 1, and that will compute and add the probability of x being 0, x being 1, and x being 2. Altogether, that probability is 99.66. So the probability of just x is 2, but the probability of all of those combined is 99. For just for demonstration purposes, I can compute binomial distribution, and this time I enter it without the dot and it still works. There are two different implementations. If we have 0 successes out of 30 and probability of 1%, non-cumulative, is 73%. That's the probability of 0. Probability of 1 is, again, binom dist with parameters successes 1, trials the same 30, probability 0.01, and cumulative is not cumulative. That's 22%, and if I add the 0 plus the 1 plus the 2 is 99.668, which is what we computed here. So this is implemented in Excel, and that helps very well. The other tool that we are going to discuss and we're going to make use of is data tables. Data tables are a tool that is designed to make sensitivity analysis. What if we change parameters in our models? The models can be very complicated, but we can change 2 parameters at a time, and we can see the effect of that in our mathematical models. So if you're not familiar with it, I'm just going to make a very simple example here. Let's say that you have 2 variables, a and b, and those variables could have any numbers associated to it, say 3 and 4, and an output is the ratio of a divided by b. Now we want to be able to analyze what would happen to that ratio if we change the parameters. So what I'm going to do is I am going to need a region for which I am going to work with, and in the top left corner, and I'm using, you don't have to highlight these in colors or anything, this is just for purposes of the video. But here in the top left corner, I'm going to enter the value by reference, that is using a formula, of the output that I want. Then on the top row, which I'm going to highlight in a different color, is, let's say that we want those to be A, the possible values that A could have. Again, you don't have to type in the A name, it's just for purposes of the explanation. And let's say that the feasible values for A are 3, 4, and 5. Whereas the possible values for, and I'm going to highlight this most left column, let's say the possible values for B are 2, 4, 6, 8, 10, and 12. So if that's the case, I can obtain all the possible combinations of 3 divided by 2, 4 divided by 2, 5 divided by 2, and enter those in their corresponding cell. So in order to be able to do that, I highlight the whole table, including the parameters and the output cell, and I select data, what if analysis, and the third option is data table. In the data table option, I get a little window that says what is the row input cell, and that refers to the top row on this cell, on this range. Right now has values 3, 4, and 5. They are associated with the value of A in the model, so I select that cell. And the most left column is associated with the value of B, so I click on that cell, K4, to indicate that those values in the most left column would be operating as the parameter indicated in the cell K4. And just hit enter and you see Excel computes all the combinations. I am going to just make it more readable, and now you have a very nice table that indicates what happens when two parameters are changed in our model. So by using these two tools, we can create operating characteristic curves. Let's start with our model here. We don't need any of this. We already built in this region a model, and now I can use that model to create a sensitivity analysis table. I'm going to use again colors. In the most left top corner, we're going to have that blue cell. In the top row, I'm going to indicate in green, and the most left column I'm going to indicate in green as well. I'll zoom out a little bit now that you understand what's going on. I don't need that. I don't need any of that. No borders and no fields. Now I have this region here. I can include a grid, and I select, well, no, first I need to make reference to the output. The output I'm interested in is the cumulative probability as a function of two things. First, maybe I want to change n. And I can say if I'm going to have fixed the acceptance number 2, but I'm going to be changing n. And we are going to be changing the proportion of non-conformities. So we can highlight that table and select Data, Quantitative Analysis, Data Table. The top row is going to be associated with N, in this case 30, and the column input cell is going to be associated with the proportion of the effective. In this case, it's 1%. I have not yet entered the numbers, so I'm getting an error there, but I can fix that by entering the possible numbers. Let's say that I'm interested in having sample sizes of 30, or considering maybe all the way to 40, 50, 50, or maybe 60 samples, or samples of size 60. And then the proportion of the effective, we vary from 1%, 2%, and we increase at steps of 1% all the way to 12%. And now we have the complete and sensitivity analysis where when we change these two parameters at a time. I'm going to format to make it more easy to make it easier to read. And it would be nice if we could see this in a graph. So I am going to take these values and paste them as values. Okay, we have here a merge cell. Okay, let's do it again. I'm going to just take the values, and these are just the values. And the reason why I copy that is because now I need to erase that top cell. I cannot erase it from the original table because I would lose all the data. But here, because I have that missing, when I create a graph, that indicates that you have two parameters, one's indicated in the most left column, one indicated in the top row, and we can insert a chart that creates the operating characteristic curve that we were looking for. Here you see we're still computing the probability of accepting, but depending on the value of the sample size, we reduce the acceptance faster or not. In order to make these videos shorter and to the point, I'm going to cut it here, and I'm going to continue this discussion in the next video.